This is 5.4, the graph of a rational function. And we're going to be learning the objectives, how to graph a rational function, and that's it. We're not going to be solving applied problems involving rational functions due to time. We've just got to focus on what we can get done for the rest of this semester. And there's just a lot of time constraints right now. So we're just going to only focus on one objective here, graphing a rational function. Step 1, step 2, let me read through these. Step 1, factor the numerator and denominator of r, find the domain of the rational function. Step 2, write r in lowest terms. Step 3, find and plot the intercepts of the graph. Use multiplicity to determine the behavior of the graph of r at each x-intercept. Step 4, find the vertical asymptotes and graph each vertical asymptote using a dashed line. Determine the behavior of the graph of r on either side of each vertical asymptote. Step 5, find the horizontal and oblique asymptote. If one exists, graph that asymptote using a dashed line and then find points, if any, where the graph of r intersects the asymptote. Plot the point. Step 6, use the real zeros of the numerator and denominator of r to divide the x-axis into intervals. Determine where the graph of r is above or below the x-axis by choosing a number in each interval and evaluating r, and then plot the points. And step 7, use the results in all of these steps to graph r. Okay, now starting here with number 1. First thing we're going to notice is we want to try to put this in lowest terms. We're going to try to reduce it. So I notice here the sum of 2 cubes is in the numerator, and in the denominator I notice I can factor out a GCF. For the sum of 2 cubes, we have a formula that we can use here. So a cubed plus b cubed is equal to a plus b times the quantity a squared minus ab plus b squared. So that means that x squared plus 1 will factor into x plus 1 times x squared minus x plus 1. And x squared plus 2x, I can just factor out a GCF of x, and that's going to leave me with x times the quantity x plus 2. So looking at these here, I notice that there are no common factors between the numerator and the denominator. So this tells me that this is already in lowest terms. Okay, so number 1, factor the numerator and denominator. We did do that. Yes. So we've got that. And since it's factored, we can find the domain. So to find the domain, you always want to do this before you try canceling out any common factors anyway and trying to reduce it in those terms. To find the domain, you just want to, whatever is given to you originally in the problem in the denominator, that's what you want to use originally. Do not try to cancel out anything first. So here we have x times x plus 2. And even though in this particular problem nothing canceled out, right? But in a future problem, if something were to cancel out, you still would want to go back to the original problem before you try canceling any common factors. So I'm going to set both of these factors equal to 0. If I set x equal to 0, I just get x equals 0. If I set x plus 2 equal to 0 and I solve it, I'm going to get x equal to a negative 2. And those are going to be my restricted values on my domain. So I want to make sure that I state my domain and I do not include those values. So it's going to be the set of all x such that x cannot equal 0 and x also cannot equal negative 2. If I want to write this in set, that was set builder notation. If I want to write this in interval notation, I'm going to draw a number line for my visual learners to help them out. I'm going to draw open circles on negative 2 and 0. And basically I'm saying I could have any other value except negative 2 and 0. That's going to be the open interval from negative infinity to negative 2, union open interval from negative 2 to 0, and union open interval from 0 to infinity. So that's going to be my domain. I'm going to erase that number line because we don't need that number line. We only wanted it to help us figure out how to write the domain in interval notation. All right. The next step, step 2, I believe, was making sure that your function is written in lowest terms. for us, in this particular example, this is already written in lowest terms. I cannot reduce it because there are no common factors. So I'm just going to go ahead and write G is in lowest terms. All right, step 3, find the intercepts. The intercepts means we're looking for the X-intercept and the Y-intercept of this function. So if you recall, you guys should already know how to find the intercepts of a function. If we're trying to find, for example, let's say the Y-intercept, then I would have to substitute 0 for X, right? And if I want to find the X-intercept, then I would substitute 0 for Y and solve for X. So that's all we basically have to do here. So let's go ahead and do that. Why don't we start off with how to find the Y-intercept? To find the Y-intercept, we're going to substitute X equal to 0 and solve for Y. So basically, we're just going to find what is G of 0. G of 0 is equal to the 0 cubed plus 1 over 0 squared plus 2 times 0. So do you guys see a problem with this? You should. You should have realized that as soon as I plugged in 0, that 0 was one of my restricted values from my domain and that this is not allowed. But I did this for some of you guys who might have missed it, that this was a restricted value, because sometimes that happens and that's okay. As long as you realize, hey, I shouldn't have done this. Now that I did do it, I should have realized, hey, that's not a good value to choose, right? And then look back at your domain and you're like, oh, 0 was a restricted value for the domain. What does this mean? This means that there is no Y-intercept. Okay, so since there is no Y-intercept, let's forget about the Y-intercept and let's focus on finding the X-intercept. So in order to find the X-intercept, what are we going to have to do? To find the X-intercept, yes, you guessed it, we're going to have to substitute Y equal to 0. And there might be more than one X-intercept. We don't know. I'm going to put an S there in parentheses just in case there is more than one X-intercept, but there might be more than one. We're going to substitute Y equal to 0 and solve for X. So instead of the G of X, I'm going to replace that whole G of X with a 0 and set that equal to the X cubed plus 1 over X squared plus 2X. Now let's solve this rational equation. I'm going to multiply both sides by the GCF of the denominator. So I'm going to multiply both sides by basically my denominator, x squared plus 2x. This is going to end up giving me 0 is equal to x cubed plus 1. So because this is the sum of two cubes, I'm going to write this factored out. 0 is equal to x plus 1 times the quantity x squared minus x plus 1. X plus 1 equal to 0. That's an easy one to solve. The second one is a quadratic. I'm going to have to think about that one for a little bit. For my first solution here, we're going to get x equal to -1. So that's going to be one of my X-intercepts. Possible X-intercepts. I don't know if there's any more. We're checking to see if there's more. I'm going to find the discriminant before I plug into the quadratic formula, because I can already tell this isn't factorable. And I just want to check and see if I should even bother wasting my time trying to use the quadratic formula. The discriminant to -3, because it's negative, that means there are no real solutions, because this -3 is the number that would appear inside the radical, inside the square root. And if you end up with a negative inside of a square root, then that means there are no real solutions. So because we're working with functions on the real number line, I'm not even going to bother wasting my time using the quadratic formula. There is only one X-intercept, -1, 0. and there is no y-intercept. So I'm just going to go ahead and write this out, and I'm just going to go ahead and box this in. All right, it looks like I need some more space. Why don't I go ahead and create a little bit more space here for me so that I can have more room to write. Okay, we're ready for step 4. We have step 1, step 2, step 3. Step 4 says find the vertical asymptotes and then graph each vertical asymptote using a dashed line. Determine the behavior of the graph of R on either side of each vertical asymptote. Okay, let's find those vertical asymptotes. I already have them right here. So when I was worried about finding the domain, and I ended up here with these two restricted values, x equal to 0 and x equal to -2, those are actually the equations of my vertical asymptotes. So I'm just going to go ahead and copy those down. VA is going to be my abbreviation for vertical asymptote. And I'm going to put here x equal to 0 and x equal to -2. And we are done. All right, I'm not going to be plotting anything on the graph until the very end. So I'm going to wait till the very end to do all the plotting and all the graphing of the dashed lines. All right, for horizontal, I'm going to look at the leading terms of these of this numerator and this denominator. I've got x cubed over x squared. Do you guys recall from our last section what this means? Yes, this means we have an oblique asymptote or a slant asymptote when the degree of the numerator is exactly 1 unit bigger than the degree of the denominator. That means we're going to have to do some long division, some polynomial division, in order to find the equation of that slant or oblique asymptote. So let's go ahead and set this up. I need more space. So this is going to be our step number 5. All right, let's go ahead and I'm going to write out what I'm actually doing here for step 5. I'm going to find the oblique, or another way to say oblique, slant asymptote. So g of x is equal to x cubed plus 1 over x squared plus 2x. I'm going to divide the polynomial that we have in the denominator into the polynomial that we have in the numerator. In order to divide these, I'm gonna have to multiply here this divisor by x in order to be able to subtract those x cubes and get them to cancel out. So we're going to cancel out the x cubes, and then we're going to be left with a -2x squared plus 1. Now I'm going to put up here a -2 because I need to multiply that x squared by a -2 in order to cancel out that -2x squared. Now we're going to distribute that -2 to each one of those terms. That's going to give me a -2x squared minus 4x. All right, we're left with a 4x plus 1. Now here I can already tell there's no way I'm going to be able to multiply by something here to get to cancel that 4x. So this 4x plus 1 is my remainder. I'm going to write it over the divisor. So I really don't need that part. The part that I need is the part that is in front of that remainder part. So I need this x minus 2 part. So the equation of my oblique asymptote is going to be y equals x minus 2. Okay, we found that. Excellent. We already mentioned in our last section, I believe, that if you have an oblique asymptote, then you can't have a horizontal one also, right? It's either one or the other. So done in terms of finding the horizontal oblique asymptotes. Step 6, use the real zeros of the numerator and denominator of r to divide the x-axis into intervals. And then determine where the graph of r is above or below the x-axis by choosing a number in each interval and evaluating r. So I'm going to, in order to do this, because this is actually like a lot of steps here within this step 6, in order to keep this nice, neat, and organized, I'm going to create a chart. I need more space for this chart. So let's create some more space in here. And I'm going to draw a chart here. Actually, before I draw my chart, I'm going to draw a number line so that I can figure out how big my charts should be. So I'm going to divide this number line using the values I got for any vertical asymptotes and also the values I got for any X-intercepts. So here I've got -1, 0 for an X-intercept. So I'm going to use that -1 to help me divide my number line, that 0 of -1. I'm going to use the values that I got here for the vertical asymptotes, x equal to 0 and x equal to -2. So I'm basically going to divide my number line here into like, using these 3 numbers. It will end up creating 4 different intervals in my number line. So do you see the 4 intervals in there? I'm going to have an interval from -∞ to -2, one from -2 to -1, then from -1 to 0, and then from 0 to infinity. I'm going to put open circles on the -2 and the 0 because those represent the asymptotes, and I want to make sure it's clear that there's no way that x is going to be able to ever equal those values. I'm going to do a closed circle though on the -1 because the -1 represents a 0. It represents like an x-intercept. So our function is allowed to be equal to that number. All right, now we're going to choose test points that are within the intervals. So some of the test points that we can choose here, we're going to choose one test point for each one of these intervals. In the interval from -∞ to -2, I'm going to choose -3. In the next interval, I'm going to choose -1.5. In the next interval, I'm going to choose -0.5. And then the last one, I'm just going to choose a 1. Okay. Now we make our chart so that we can write out all of this good stuff that we got from here, from our using these test points. We're going to find out some good information that's going to help us be able to graph this rational function. So this first row here is going to represent the intervals that I created here. There's one interval, the open interval from -∞ to -2. And then my next interval is going to be from -2 to -1. And I'm just going to do open on -1, even though it's closed there, because I'm really looking for a number between those two. I don't want to accidentally choose that -1 because I'm trying to choose a number that's in between those two values. And then the other 2 intervals were the open interval from -1 to 0 and the open interval from 0 to infinity. All right, now the number that I chose that was within the interval, I got -3, -1.5, -0.5, and 1. Next, we're going to choose the value of g at that given, that number chosen. So we're going to find g of -3. Let's find out what that equals. We're going to find g of -1.5. We're going to find g of -0.5 and g of 1. Yes. Now, for the next row, we're going to find the location of where does it show up on the graph. Is this value that we got that for our test point, when we plug it in, does it come up above or below the x-axis? Okay, so that's what that means when it says location of graph. And then the last thing is going to be the point on the graph. So it's going to be basically an ordered pair. So like -3 comma something. This will be -1.5 comma something. -0.5 comma something. And and this is just +1 comma something. All right, let's go ahead and use our calculator to come up with these values. So I'm just going to go ahead and figure this out by just, doing a little bit of plug and chug, plugging it into the calculator and getting my numbers here. So let's go ahead and plug in -3 into our function and let's see what we get. Let's go back and find out where was our original function. I forgot it already. Okay, I found it. I'm going to go ahead and just plug it into my calculator right now. See what I get. You guys, while I'm plugging it in, you guys are doing this in your calculator too. Okay, so that way you can double check my work. So for g of -3, I got -26/3. For g of -1.5, oh, before I go that, let me rewrite this as a mixed number because that might help us when we're graphing. And then we also write it as a decimal in case anyone wants to see it written as a decimal. Okay, so now that we got all that, I can see that I got my negative value there for that -26/3, or we could also say -8 2/3, right? For the next one, g of -1.5, I got +19/6, which is also the same thing as 3 1/6. Or 3.16 with a repeating bar on it. And then g of -0.5, if we go ahead and plug that into the calculator, we get -7/6. And that's the same thing as -1 1/6, or -1.16 with a repeating bar on it. And then we've got g of 1, and if we plug that in, we get 2/3. And 2/3, well, I'm just going to write it in decimal. I can't write that as a mixed number, right? Because it's a proper fraction. I just get 0.6 with a repeating bar on it. Now I'm going to look at the signs, because this is going to determine the location on the graph. So this first one, it's negative. That means it's below the x-axis. So when I'm drawing my graph, I know that this part has to stay below the x-axis. And then this is positive, so this one has to be above the x-axis. This is negative, so this is below the x-axis. And the last one is positive, so that means it's going to be above the x-axis. And I'm going to go ahead and write each one of these as ordered pairs as well here. There is my table. So I filled everything in. Now that I've filled all this in, right, I'm ready to start coming up with the graph to this function. This was step 6. We're going to use all this great information that we got in all of these steps to help us come up with the graph of this function. See, what does the graph of this look like? Remember, the whole goal of this, I know you guys have graphing calculators, but the whole goal is we're trying to learn how to graph without a graphing calculator. And I told you guys that this is helpful because it's not good to just be completely reliant on the graphing calculator all the time. It's nice to know how to do things also by hand. And so let's go ahead and do this. This is going to be our step 7, and this is going to represent our graph. Okay, so we're going to go ahead and draw our graph right here. This is going to represent my y-axis. And then I'm going to draw my x-axis. Okay, maybe not yet. Maybe first let me count and see how how high I have to place my x-axis to make sure I can fit all my points on there. I think this should fit. This should work. So this is going to represent my x-axis. I'm going to start off by drawing my vertical asymptotes. So this is x equal to -2. So I'm going to label it. You can label your x or your vertical asymptotes by writing the equation either at the bottom or at the top of the line. I tend to always want to label them at the bottom, but sometimes I'll label them at the top. But for the most part, I tend to label the equations at the bottom for vertical asymptotes. And then you represent it with a dashed line. So those are my two vertical asymptotes. My oblique asymptote was y equal to x minus 2. It has a slope of 1, so that means it has rise 1, run 1, and a y-intercept of 0, -2. So this is what it should look like right here. Once again, I'm drawing a dashed line, and I'm going to label this dashed line with the equation of that oblique asymptote. There we go. Okay, so now I'm going to start labeling some of these important points that I was able to come up with to help me draw this graph. Okay. All right, so we're ready to start plotting some points. Let's start off with that X-intercept. That's at -1, 0. Let's go ahead and plot our point there, and we will label it so it looks nice and labeled. All right, let's go ahead and plot another point. How about that -3, -26/3? But instead of -26/3, I'm going to use the mixed number version because that'll be easier for me to find. So -3, and then comma, let's use 8 2/3 instead. And that's going to be right about here. Remember, this is a sketch and it doesn't have to be perfect. It's just to help us, you know, in finding some points that are going to be on this graph to help us draw a sketch of this graph. All right, let's go ahead and graph. How about -1.5 19/6? But instead of 19/6, I'm going to use 3 and 1/6. Now, I accidentally wrote a negative here, so that's why you saw that I put an annotation on top of that, and I put the approximation, the 3.17, because it's easier for me to use a decimal approximation. I accidentally wrote -3 and 1/6, but it should be a +3 and 1/6, right? There, you can see it there. You can see my mistake. It was very late at night when I did this video, and I was writing it out, and I wasn't paying attention. It's a little mistake, but please, 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 don't do that on your notes. All right, now that I talked about that, let's go ahead and finish plotting these points. How about -0.5, -1, and I think that's -1 and 1/6. Now, there was a part on step 5 that I forgot to do. Our functions can sometimes they cross our horizontal and our oblique asymptotes. I forgot to do that one part. Oh, well, first let me finish plotting this one point right here. This is at -1, -1, 2/3. But like I was saying, sometimes our functions will cross oblique and horizontal asymptotes. And in order to find that point of intersection, if there exists one, we're going to need to set our function equal to the equation of our oblique asymptote. So I'm going to do that step here. So this was actually part of step 5 where it says find any point of intersection. So this is my function. G of x is equal to x cubed plus 3 over x squared plus 2x. And then this is my oblique asymptote equation. Y is equal to x minus 2. I'm going to basically set these equations equals to each other. So I'm going to set x cubed plus 1 over x squared plus 2x equal to x minus 2. And I'm going to solve this equation. If there is a solution, then that means that there is a point of intersection between these two. Okay, so in solving a rational equation, I'm going to multiply through by the GCF of the LCD. And then this is going to leave me with x cubed plus 1 is equal to, I'm going to go ahead and distribute this out or use the FOIL method. And this is going to leave me with a 1 is equal to negative 4x. If I divide both sides by negative 4, I'm going to get x is equal to negative 1/4. That means that there is a point of intersection. The point of intersection is going to have an x coordinate of negative 1/4. In order for me to find the y coordinate, I'm going to have to take this x coordinate and I'm going to have to substitute it back into the equation of the function. So I'm going to basically have to find g of negative 1/4. Okay, it's a little bit more work, but that's okay. We can do this. It's to help so that our sketch of our graph can be as accurate as possible, right? Doesn't have to be perfect, but we do want it to make sure that it's clear where it's crossing, if it is crossing at at any of the asymptotes. And in this case, it is crossing at one of the asymptotes. Okay, g of negative 1/4. What's that equal to? I'm just going to put this into the calculator. I get negative 2.25. All right, so that means our ordered pair is going to be negative 1/4, comma, negative 2.25. And this is going to be right about here. All right, I think I have enough stuff here to go ahead and start graphing this. I'm just going to start connecting some of these dots. Now remember, our function cannot cross the vertical asymptotes at all because it would be undefined, right? So it's going to get very close to this vertical asymptote right here, and then it's going to come down a little bit, cross at the horizontal. That's okay. It can cross at a horizontal. And I'm going to draw my arrows at the ends. Now the ones that are over here, we are positive it's not going to cross the vertical asymptote, and it's not going to cross the oblique asymptote either, because we went through all the trouble of finding which points it would cross at the oblique asymptote. So I'm just going to make my function line up as closely as I can here to my oblique asymptote, but it's not going to touch it. And it's going to line up on the other side right here as very closely as I possibly can to the vertical asymptote on the other side. And I'm going to do the same thing over here on the other side. I'm just going to use this point, this one point that I have here. You could probably come up with a few other points if you need a few other points to help guide you. But I'm going to use this one point to guide me. Once again, it's going to get very, very close to my vertical asymptote. Right here, going towards the right. And then going to the left, it's going to get very, very close to the oblique asymptote, but it's not going to touch it because we went through a lot of trouble to figure out at what points this function crosses that oblique asymptote. And we only came up with one. It only crosses at one point. So there it is. That's our function. Wasn't that fun? That was lots of fun. I know. Now you should check this on your graphing calculator to make sure you did it correctly. So after you're done doing the sketch by hand, where you practice doing all of these techniques we just talked about to make sure that you aren't just dependent on the calculator and that you know how to do these by hand, plug it into your calculator to double check your work to make sure you actually didn't make any mistakes, okay? You might have to adjust your window, the graphing window on the graphing calculator, to make sure that the entire function comes out nicely. So make sure you guys do that. All right, let's go on to the next problem. Number 2, g of x is equal to x squared plus 3x minus 10 all over x squared plus 8x plus 15. Yay! Step 1. Let's factor this thing out. Because these have leading coefficients of 1s, I'm just going to go straight to the factors. I'm not going to do the factoring by grouping method, but if you need to do the factoring by grouping method, then you go right ahead. That's okay. You can do that. So the factors for the numerator are x plus 5 and x minus 2. And the factors for the denominator look like they're going to be, let's see, we need two numbers that multiply to give 15 and add up to give 8. What are those two numbers that multiply to give 15 and add up to 8? I think we can use 5 and 3, yeah. So I'm going to write those factors out, x plus 5 and x plus 3. We can only do this shortcut here when we have that leading coefficient of 1, right? That's why I'm not doing the factoring by grouping method. Now, I can see what it would reduce to, but actually before I reduce it, let me take that back. Let me not reduce it just yet. First, let me set each one of these factors equal to 0, because remember, I mentioned this in the last problem, but I don't know if everyone caught it. You need to take all of the factors that you have in the denominator before you reduce and set those equal to 0 to figure out what your domain is. This is very important. You can't just ignore that factor of x plus 5 and pretend like it just magically disappears. So our domain here is going to have two restricted values. X, the set of all x, such that x cannot equal -5 and x cannot equal -3. And we could also write this in interval notation as the open interval from -infinity to -5, union the open interval from -5 to -3, union open interval from -3 to infinity. All right, now I'll do that step 2 where I reduce. I'll write it in lowest terms. So notice that we do have two steps for this. One step, we factor it, we find the domain, right? And that was written right up here. Oh, I'm sorry about that. I don't know why I did that. And let me make this smaller so I can make some more space right here. So step 1 was where we factor it. We find the domain given the factors that were given to us originally. And then step 2, a separate step, that's where we reduce it. It's very important that you realize these are like two separate steps, okay? Because otherwise you would lose that factor of x plus 5, and that x plus 5 factor is very important. Now here, what does this x plus 5, the fact that it cancels out, what does that mean? It means we have a hole. We have a hole at x equal to -5. That's what it means. So this function is basically going to look just like g of x is equal to x minus 2 over x plus 3, but we have a hole at x equal to -5. If we substitute x equal to -5 into the reduced version, the one that's in lowest terms, then we can find the ordered pair that is associated with that hole. It's very important that you substitute it into the reduced version, into the one in lowest terms. Why, you ask? Because if you substitute it into the original version, then it would be undefined, because x equal to -5 is a restricted value in that original version, right? So when we get g of -5 and we plug that in, we end up with +7/2, which is the same thing as 3.5. I think I'm just going to go ahead and stick with the decimal version here. So we're going to have a hole at -5, 3.5. This is important because if you're sketching a graph of this rational function, you're going to want to make sure you label this hole. This hole is going to be an important part of that graph. Step 3, let's find the intercepts. So we already know how to find x and y intercepts, right? We can substitute 0 for x and then solve for y to get the y. And then we can substitute 0 for y and solve for x to get the x intercept. All right, let's do substitute 0 for x. G of 0 is going to be equal to -2/3. So our y-intercept is at 0, -2/3. Now let's find the x-intercept. Substitute 0 for the y and solve for x. 0 is equal to -x minus 2 over x plus 3. and I'm going to multiply both sides by x plus 3, and then that's just going to give me 0 is equal to x minus 2. And if I solve for 0 is equal to x minus 2, I'm going to end up with x equals positive 2. That means we have an X-intercept at 2, 0. Yay, we found our intercepts. So now, all right, we're ready for step 4. Let's go ahead and write this down for step number 4. We're going to have to find the vertical asymptotes. Now, normally when I found the vertical asymptotes, I usually just look at my domain and I say, well, what were my restrictions on my domain? But this is a very special example here, because remember that one of those restrictions ended up being a hole. A hole cannot be a vertical asymptote. It can't. Okay? So you have to keep this in mind. If you do find that domain and you do find those restricted values, if any of those restricted values ends up being a hole, you've got the same factor in the numerator and denominator and they end up canceling out, that's not going to fall into the category of vertical asymptotes. Okay, so I don't want to include that x equal to -5. That is not going to be a vertical asymptote. The only vertical asymptote here in this example is going to be at x equal to -3. And that's it. That'll be my only one. Let me go ahead and write VA next to it so it's very clear this is a vertical asymptote here. And that's it. All right, step number 5. Step number 5 says we're going to look for any horizontal or any oblique asymptotes. Remember, you can't have both of them, right? It's possible to have neither, but you can't have both. So what we're going to do for this step number 5 is we're going to look at the leading terms of our polynomials in the numerator and denominator. So let's look at those. We're going to look at the degrees of those. We're going to compare them. If I look at g of x and I look at the leading terms in the numerator and denominator, I see x squared and x squared. They both have the same degree. So we said when they both have the same degree, when n is equal to m, remember we were talking about this in that last section we're working on, this means you have a horizontal asymptote. You're going to take the coefficients, which in this case would be a 1 for the x squared in the numerator and the 1 for the x squared in the denominator. I'm going to write that as a fraction there, and we're just going to have y is equal to 1. So our horizontal asymptote is just going to be a 1. And that's it. That's it. We're done with that part. We're done with, I know these problems take a long time. That's why we only have very few examples for these notes, okay, you guys? So I recognize that these problems take a long time, but it's important to know the steps of how to do this. Now I'm going to need more space, so I went ahead down here and I created a table down here to do the next part down here, and also to do that step number 5 continued here. So remember that one step number 5 part that I forgot in the first example? I'm not going to forget it here. I'm going to look to see, are there any points of intersection between our function and our horizontal asymptote? I'm going to set these two equations equal to each other and I'm going to solve. So it's a rational equation. I'm going to multiply both sides by that LCD. So it's going to be multiply both sides by x plus 3. I'm going to get x minus 2 is equal to x plus 3. The x's cancel out. I'm left with -2 is equal to 3. This equation says that there is no solution to this. Therefore, what does that mean? There are no points of intersection between my function and my horizontal asymptote. And that's it. That's all there is to it. All right, excellent. And I'm so glad I didn't forget to do this step here where it's supposed to go. Now, I know these steps, you know, some of you guys are thinking, oh, do I have to do these steps? I'm like, no, you don't have to do it in these steps. If you want to do things in a slightly different order, you can totally do that. These steps are just a guideline to help you for the people that need steps. Because there's some people out there that need, hey, this is step 1, this is step 2, this is step 3, and it's more for those people. But if you already know everything that you're supposed to do and you want to do things in a slightly different order, you are welcome to do that as well, which is what I sometimes tend to do. All right, I'm going to go ahead and draw my number line here. I'm going to label it with all these important values that we have here. We have -3. That's an important value because that represents my vertical asymptote. And then 2, that was my X-Intercept. All right, I'm not going to use my whole here. I'm going to then choose test points, -4, 0, and 3. So this is going to split my number line up into basically 3 intervals that I'm checking here. I copied and pasted the last table I did. So I took off 1 extra row there. There was 4 columns, but I made it into 3. 1 interval is going to be the open interval from -infinity to, that was supposed to be a -3 on there. Please write in the negative. Ugh. And yeah, and you guys can see the rest. I always get distracted once I make one of those little careless mistakes. It tends to distract me. But you guys can see where I was setting this up, right? Good. All right, let's go ahead and substitute these values. Let's find out what g of -4 is. Let's just go ahead and use the calculator. Just plug it into the calculator and get that value. Now, you guys here, you guys can choose to use the original function, or you could choose to use the reduced function, because basically our function is going to look just like the reduced one, except it's going to have a hole in it. Okay, so if it were me, I would just use the reduced version of the function because it's easier, it's less work. So I'm going to use g of x is equal to x minus 2 over x plus 3. And so that's going to give me -4 minus 2 over -4 plus 3. And g of -4 is going to come out to -6 divided by -1, which is +6. This means that since it's a +6, that this point is going to be above the x-axis. G of 0, when I substitute g of 0, I'm going to get 0 minus 2 over 0 plus 3, which is -2/3. Because g of 0 is equal to -2/3, it's a negative value. I know it's going to lie below the x-axis. This is very helpful, you know, to know the location where it's going to be on this graph, because it's going to help you when you're drawing this sketch. You know, it's important to know whether you're above or below the x-axis. G of 3 is going to come out to 3 minus 2 over 3 plus 3, which is 1/6. It's a positive number, so it's above the x-axis. And there we go. There you have it. We're ready to draw our graph. Yay! Yeah. All right, so here's my graph. I'm going to go ahead, and I always like to start off with any vertical or horizontal or oblique asymptotes that I might have. So that's where I'm going to start off, drawing dashed lines to represent those asymptotes. And I like to label them with the equations. I usually like to label the equations below the line, but you could also label it up on the top part if you want. So there is my vertical asymptote for x equal to -3. I'm going to, you know, I can see that I'm not going to have enough space here to make a nice accurate graph. So I'm going to erase my work from right here. And I'm going to extend my line. As soon as I can get rid of that little 3 Pesky little 3. Get out of there. There we go. All right, so here goes our horizontal asymptote at y equal to 1. I'm going to label it with the equation. I like to label those equations for my horizontal asymptotes on the sides. Either you could do it on the left side or on the right side. I tend to like to write my equations for my horizontal asymptotes on the right side for some reason. And now we're ready to go ahead and label our intercepts. So there are our intercepts I labeled. And this is going to be here. My hole that I labeled right there. I'm going to plot it. Well, I'm going to also label it with the coordinates in a minute. And then here's another point. This is our point for -4, 6. And I think I have one more point right over here. And this point right over here was at 3, 1/6. There, I think that's pretty good. I think that's enough for me to draw a nice little sketch here. Now, since I know it's not going to cross y equal to 1 because I went through all the trouble of looking for that point of intersection and I didn't find one, I'm just going to make it go very close to my asymptotes. It's going to get very close to my vertical asymptote. It's going to get very close to my horizontal one, but it's not going to touch. I'm going to label my ordered pairs for my points right here. And then over here on this side, once again, I know it's never going to touch my vertical asymptote over here, so it's going to get very close. And the same thing with my horizontal one. I went through all the trouble of checking to make sure it wouldn't touch the horizontal one, and it doesn't. And I'm going to label my ordered pairs. Perfect. Beauteous. It's glorious. I'm done. Wonderful. Now what do? You're not done until you check it on your graphing calculator, right? Because the whole point of this is to make sure that you are doing this correctly, right? All right, number 3, find a rational function that might have the given graph. More than one answer might be possible. So here we're going to have 2 vertical asymptotes, one at x equal to -1 and one at x equal to 1. That means that I'm going to need factors in the denominator, like in the form of x minus r, but instead of r, I'm going to replace the r with those x values. So I'm going to put in here x minus -1 and x minus a +1. And I'm going to simplify these. It's going to simplify to x plus 1 and x minus 1. Those are going to be the factors of my denominator. I also have a 0 here, right? A 0 is the x-coordinate of the x-intercept. So I'm going to make sure that that has to be also reflected. This is going to be reflected in the numerator part of my function, of my rational function. And because it's actually crossing the x-axis at this x-intercept, it's not just touching or it bounces off, it's actually crossing. I'm going to make sure that when I write this factor of, x, and the numerator, it's got to have a multiplicity that's odd. So that's very important. So I'm going to have a factor of the numerator that's basically going to be like an x minus 0, which is just an x. And it's got to be raised to an odd power because it's actually crossing the x-axis. I'm going to make it 1 because it does say here you can't have more than one right answer. And 1 just seems like the easiest option for me here. 1 is odd, so it has odd multiplicity. So that's good. The horizontal asymptote is y equal to 0. In that case, in order to get y equal to 0, I know that the degree of my numerator must be less than the degree of the denominator. This is review from 5.3 on how to graph rational functions, right? So we were talking about those properties of graphing rational functions, I believe, and we're talking about how to find these how to determine about the horizontal and oblique asymptotes. And we said if the degree in the numerator is less than the degree of the denominator, then we would have a horizontal asymptote of y equal to 0. Okay, I think this is enough information right here to go ahead. And also look at the orientation of the way this graph is set up. If you also remember from 5.3, we also said that when it's got this flipped version, that looks like it was reflected across the x-axis, we're going to have to multiply by a negative. So I'm also going to multiply, I'll just put it in the numerator. I'm going to make it a negative x. And this is something you'd have to have memorized by looking at this to know that the orientation is flipped, that it has to be a negative x here. You could put the negative in front of the fraction bar if you want, or if you wanted to put it in front of one of the factors in the denominator, that's fine too. And that's it. We are done. That's our answer. Let's box it in. And let's call it a good job for us. Give yourselves a pat on the back. Excellent.